Okay, so let's start. In the previous class, we essentially derived the KKT conditions, which are a set of necessary conditions for optimality of a given point, assuming strong duality holds. Right. So, given any optimization problem, convex or not, you can always try to solve for the KKT conditions. Given nothing else, that's one particular approach, and this will give you a solution if you're able to solve for the KKT conditions. And there are numerical procedures that allow you to solve for these. So just to take a step back, we saw that given any optimization problem, convex or not, you can always formulate the so-called dual optimization problem. And sometimes both of them take roughly the same form. They have the same structure, as we saw in a couple of examples. For example, the linear program. If you take the linear program, the dual of the linear program is also another linear program. If you have a semi-definite program, then the dual of a semi-definite program also turns out to be another semi-definite program. And the same holds for the conic program. Right? So in terms of the complexity, solving the dual may not be any simpler. But at times solving for the KKT conditions is easier if you want to look for some kind of a closed form expression for the solution. But there are many situations wherein the dual of a given optimization problem also offers geometric or other intuitions for the original problem of what kind of a solution you may get eventually. And we'll see a little bit of that in today's class. So in today's class, I look at one sort of broad problem, which is that of linear classification. So let me formally set up the problem. In particular, so this is a fundamental problem in machine learning, and the way it's set up, one way to pose the problem is the following. You're given two sets of points in some space. So let's assume that all the points come from, say, Rn. You're given two sets of points, let's call them x and y. So the set x consists of, say, capital N points, each xi belonging to Rn, and another set y, y1 up to, say, ym, each yi is also from Rn. And the goal is in some sense to find out what distinguishes these two sets of points. Many other kinds of machine learning problems can be posed as classification problems. But in this case, our goal is to find out essentially what is the difference. Is there a simple test to decide whether a given point, some new point, lies in the first class or the second class? And so first we'll ask the following simpler question, which is of linear classification. Or sometimes called linear discrimination. Which is, given these two sets of points, can I draw a hyperplane that separates these two sets? Okay, that's a very simple geometric problem that one can try to answer. So given x and y, can we construct hyperplane, so a hyperplane, as you know, is described by 2 points, two objects. One is the normal vector and the other is the shift. Such that A transpose xi is, let's say, always greater than B, and you take any set in any point from the second set, A transpose yi is always less than B. Okay, is the problem clear? Now, of course, the more apt name for this problem is linear discrimination, because typically in linear classification, you're given a bunch of training points, which are what I have over here. But eventually, what you want is that you should be able to distinguish whether a new point which you've not observed so far lies in the first class or the second class. But in this case, I'm asking a much simpler problem, which is given two sets of points, can I draw a hyperplane that separates those two? Okay. So firstly, we don't know if there exists such a hyperplane or not. It's certainly possible that there doesn't. It is impossible to construct such a hyperplane. But if you can construct a hyperplane, then we say that they're linearly separable. Then they're called linearly separable. Okay. Suppose someone gives you two sets of points which are actually linearly separable. How do you go about constructing such a hyperplane? Yeah. Okay, so closest in what sense? Okay. Okay. Would that always work? But which line? There are infinitely many lines, right? That's kind of what he's suggesting, that you take pairwise distances between points, 1 point from the set x, 1 point from the set y, and then find out the pair of points which are closest to each other. Which hyperplane? Okay. What convex set? Which is called? Okay, you take convex hull of x, convex hull of y, and then? Correct. That's fine. So that will answer the question as to whether it is possible to construct a hyperplane or not. But how do you actually go about constructing such a hyperplane? So, of course, one thing is to answer whether you can construct a hyperplane or not. But even what you mentioned, yeah, so certainly if the convex hulls don't intersect, then you can construct a hyperplane because you have two convex sets and so therefore it is possible to construct a separating hyperplane. But if they do intersect, then why is it true that you can't construct a separating hyperplane? Okay. I'm sorry. Okay. Can you make that a little more formal?
You're asking why can't we draw a line if the convex is intersecting?
Correct. The convex hulls are intersecting. Yes.
They're intersecting means that so there is a one point of set A.
Correct. There's one point in set A. Okay. So you have the convex hull of X. Let me call that A. And B is the convex hull of the set Y.
There will be one point A
Okay.
that lies on the line drawing.
Okay. So let's suppose that there you're saying that there exists an X in A, which can be written as X is equal to, let's say, summation over I alpha I y I. Basically, you can write X as a convex combination of the y axis. Okay.
Try to build a hyperplane for B,
Okay.
and then so all the points of B will be on the left side of the hyperplane.
Okay. Let's say on one side of the hyperplane. Fine. So let's say suppose there exists some point. So A transpose Y is, let's say, greater than B for all Y in this set Y.
So since X can be formed using B, X also will be on the same side as B.
Okay. But again, you're distinguishing between two things, right? One is whether there exists a hyperplane that separates X and Y. The other thing is, does there exist a hyperplane that separates A and B? Do you get the difference? All right, because there are more points in A and B, right? The convex. But is it true that a hyperplane that separates X and Y has to separate A and B? Why?
If you take in a 2D, the convex hull of C set is the lines, the polygon formed by the joining of all these points.
Correct.
So if it is separating X and Y,
Okay.
it's not possible that it will not separate these 2 points because they are the edge.
Can you think about it in more generality? The intuition is right.
The point which is very minimum to the hyperplane
Okay.
will negate the condition.
But why is that true?
If we take 2 points on X,
Okay.
they are same side on X.
Okay. Two points from X. Okay. And the same.
So like any point on the line joining the 2 points will also be on the same side.
Okay.
Because if you take 2 points, one will be closest, the minimum will be closest.
Okay.
The closest is on the side X, then
Okay.
any point to take it from that distance to the side closest.
You're right, you're going along the right direction. So, okay, so I leave that as an exercise, just try it. Okay, try to formally prove mathematically that if, so if a hyperplane separates any two sets x and y, then it also separates a and b. The reverse is clear, right? Obviously, because x and y are subsets of a and b. If there's a hyperplane that separates a and b, then it should always also separate x and y. But you should prove that the reverse also holds. Okay, but now coming back to the question. Okay, so suppose I give you two sets which are actually linearly separable. Okay, somehow I'm generating it. I'm not telling you how I generated this set, but I'm guaranteeing that that it is linearly separable. Can we come up with an algorithm to construct such a hyperplane? What tools do we have at our disposal? Let's assume we can solve any convex optimization problem. Okay, so given any convex optimization problem, I have an algorithm to solve this. I just feed it into CVXPy for now, and I can solve it. But firstly, how do I pose this as an optimization problem? Okay, so a comma b, right? So what are our variables? Firstly, a and b are our variables. So let's list everything we know. Variables are a comma b. This is in okay. Now, if I'm able to somehow pose the linear discrimination problem as in the standard form that I have, then I'm done. Okay, so these are the variables. What do we want? You're already given the two sets of points, x1 through xn and y1 through ym. So it's easiest to start with the constraints. What are the constraints? Okay, so let's start with that. A transpose xi. So I have A transpose x, A transpose xi is less than B for all xi in this set, and A transpose yi is greater than B for all yi belongs to set y. Okay, so these are constraints. Any other constraints? I'm sorry? That the x and y are given to you. So there's nothing to optimize over. The problem is described using x and y. The constraints must be for the variables, right? What else? Any other constraints? Okay, let's say that no other constraints. But what is objective function? Between what? Difference of what distances? Okay. 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 Why? So for now, I don't care. I just want one hyperplane that separates these two. Any guesses? Let's take a step back and see what our goal is. Right. So this describes the constraint set. Correct. The set of all a comma b which satisfies a transpose xi less than b and a transpose yi greater than b for all these xi's and yi's. That is my constraint set. Now, firstly, is it okay to get any point in the constraint set? It is, right? I don't care. I mean, I'm not, I don't have any other requirements beyond this particular. So then what kind of a problem do I actually have? Linear in what? So it's okay if my optimization algorithm gives me any single point from the constraint set, right? Now suppose I had to bring this to a standard form. I just want to impose everything in standard form, right? So how would you pose this optimization problem? Every optimization problem should be of the form, let's say, minimize some function f of x subject to x being in the constraint set. Right? Now I know exactly what the constraint set is. How should I choose my objective function? Yeah? What is identity function? So I want to pose this as minimum of something subject to A transpose xi less than b and A transpose yi greater than b yi. What should I fill in here? Minimize what? Okay, so yep, so I can just minimize a constant. Right? Any constant will do. Because I'm allowing you to choose any function, right? And in this case, I choose the constant function. If suppose I have a black box algorithm that takes as input this particular problem and outputs me a solution, I'm happy. Right? So this is what is called a satisfiability problem. Give me one point that satisfies the constraint. Okay, it's a special class of optimization algorithms wherein the objective function is just the constant. Okay, so that's one point. But now, is this really in the standard form? Okay, why is it not in standard form? That's okay. I mean, I could of course rearrange these terms, but is it really, can I bring it down to standard? Carefully think about what the standard form was. Minimize f some f0 of x subject to fi of x less than or equal to 0. It's an inequality constraint, right? But here what do I have? I have a strict inequality constraints, which means that boundary points are not acceptable, right? Is it possible to represent a strict inequality constraint as an inequality constraint? How?
This condition has to be one, another.
Okay, but then would that still remain a nice convex optimization problem? It wouldn't, right? Yeah. So then what can I do? In general, it's not possible, but in this special case, as it turns out, you can do something. So let's look at this constraint set, right? I want A transpose xi less than b, A transpose yi greater than b. In fact, the hyperplane is described by A transpose x equal to b, correct? How many hyperplanes exist that satisfies these properties? Infinitely many. Always? So why do there exist infinitely many hyperplanes or infinitely many solutions to this particular statement? There is no restriction. What do you mean by the boundary points? Okay, but hyperplane is described by the normal vector and b, nothing else. Okay, suppose that there exists a unique hyperplane that separates these two. Okay, in that special case, do there still exist infinitely many solutions for a comma b? Not parallel, but I mean, think about it, right? So the set of all, the hyperplane is described by the set of all points satisfying A transpose x equal to b, right? So basically, if I scale A and b by the same amount, I get the same hyperplane, correct? So now I have to be a little careful, right? Because essentially scaling both of these gives me the same thing. So there will exist infinitely many solutions. I somehow want to restrict my search space. Okay. Divide by. Okay. So basically, you can restrict yourself to b equal to 1. Correct. What do you mean by regularize? Okay. Sorry. Okay, so that's one way to do it. I restrict myself to putting some other kind of constraint on A and B. Of course, I could impose that the 2 norm of A equal to B, but that will not end up being a convex optimization problem, right? Because for a convex optimization problem, the only equality constraints I allow are affine constraints. Okay, so I'll pose this in a slightly different way. I'll say that my problem is to minimize. Again, my variables are a and b. I minimize a constant function subject to the following constraints, that A transpose X is, let's say, greater than or equal to B plus 1. Xi is in the first set, and A transpose Yi is less than or equal to B minus 1 for all yi in this set y. Why is this okay? Correct. So it's almost as though I put A transpose. So I have A transpose Xi greater than B, and A transpose Yi is less than B. I could instead put a small delta, right, where I want to demand that delta is strictly greater than 0. Correct. But if I do so, I have another constraint for delta, that delta should be strictly greater than 0, which I want to avoid. In this special case, because scaling both A and B by the same amount gives me the same thing, and these are linear constraints, I can essentially fix the delta to be some constant, some positive constant. I just fix it to be equal to 1. All right, is that reasoning clear? Okay. So now I have an optimization problem. This is in the standard form. It is a convex optimization problem. So I can solve for this. Right? So let's try to do that. Right? We already have a tool for solving such convex optimization problems. Let's go ahead. So for this purpose, I'm going to generate a bunch of points. Let's say I generate 30 points at random, completely at random, and I'm going to split them into 2 sets based on some particular hyperplane. I'm going to construct a hyperplane, and whatever lies on one side of the hyperplane, I'm going to put it in one set, and all of the points that lie below the hyperplane, I'm going to put it in another set. Okay, so that is my ground truth. Right? That hyperplane is my ground truth. And this is what that looks like. This is one example. So all the green points, you can see it clearly, all the green points is, let's say, set X, and all the points marked by crosses, all of these correspond to the set Y. And the ground truth is described by this particular hyperplane. So now let me set up the optimization problem. I have 2 sets of variables, A and B, correct? And my objective is to minimize a constant subject to constraints, which is x1. So I'm calling the 2 sets x1 and x2. In this case, x1 is an array. It's a whatever. It's a d by n by 2 array, and x2 is another m by 2 array. So this, when multiplied with a, should be, say, less than or equal to b, and x2 multiplied with a should be greater than or equal to, less than or equal to b minus 1, be greater than or equal to b plus 1. Okay, so I just try to solve for this. And I get some solution. Let me try to see what the solution looks like. For this, I'll plot the same set of points along with the hyperplane that I obtained by solving it using CVXY. We call Z1, Z2. Which is so recall that the dotted line represents the dashed line represents the ground truth, and by solving this particular optimization problem, I got this continuous line, straight line. Okay, the solid line represents the solution from the given optimization problem. Now, this does not exactly correspond to the ground truth because it is one solution, right? One hyperplane that separates these two. Now, if I wanted to get something even more close to the ground truth, then I would have to possibly generate more points. I could generate, let's say, 150 points and solve this particular optimization problem. I plot the two, they essentially overlap. Okay, so all of this is well and good. Now suppose I want to think of a better solution. Right? So let's try to explore other ways of trying to solve the same problem. Now you had some kind of a geometric intuition as to how to construct the hyperplane, right? And what was that? Correct. So basically you take the convex hull and you look at the sort of the minimum, the 2 points between which are closest between the two sets and try to construct a hyperplane that passes through the middle, right? That was one intuitive way of generating such a separating hyperplane. Let's try to think about such an approach. But even here, I effectively wanted to so right here I just want I could have chosen this to be say less than some particular b plus delta, sorry, b minus delta. This is greater than b plus delta. So one way of constructing a hyperplane is to sort of maximize or try to construct that hyperplane which is in some sense at the midpoint between these two sets. Correct. So let's try to do that. So let's say let's go back to the constraints. Recall that. So let's take another approach. Okay. So I'll introduce another variable, which is my delta or t, as I'll call it. So I'll demand that A transpose X should be less than or equal to, say, B plus B minus T for all xi in X. I'll want A transpose Yi greater than or equal to B plus T for all yi in y. I'll of course want t to be greater than or equal to 0, but just this is not enough. So I'll instead demand that the norm of a should be less than or equal to 1. That takes care of the scaling problem. Note that I'm saying the 2 norm of a is less than or equal to 1. Okay, but now I have another new variable t, right, which in some sense can be interpreted as the separation between the two sets, right? Because the norm of a is fixed right now. I don't have too many hyperplanes that describe the same, or too many a comma b's that describe the same hyperplane. So one way of interpreting this particular formulation is that I add a buffer area around the hyperplane of plus t and minus t. So I'm giving two sets of points. This is one set. This is another set. And there can be multiple hyperplanes that separate these. So this is one such hyperplane. But I'm also adding a kind of a buffer on both sides, which is this kind of a buffer, and the width of this is basically going to be equal to t. This is my t. So now I can try to get the most buffer possible. So now what would be my how would I frame my optimization problem? Correct. So the problem would then be maximize t or minimize minus t subject to this set of constraints. All right. Yeah. Otherwise, this t gets shrunk, right? Because I'm saying that if I don't impose a constraint on the norm, then I could scale a and b up by some amount, right? So if I could potentially multiply both a and b by alpha, let's say, and I would get alpha times this less than or equal to this, or that's the same as saying that alpha transpose a transpose xi less than or equal to b minus t by alpha, and a transpose yi is greater than or equal to b plus t by alpha. And in this case, as I increase alpha, this quantity decreases to 0. So effectively this would be the width, right? And the width would shrink to 0. So then this would not really be the true sort of buffer size. So here's another exercise. Suppose that the norm of a is actually equal to 1. Okay, so you take a hyperplane. So consider any hyperplane. Set of all x such that, say, a transpose x minus b is, let's say, between minus t, and plus t. This is the region in between those two. Correct? And you impose the constraint that the norm of A is equal to 1. Okay. For this, find out what the minimum distance to the hyperplane will be equal to. Okay, or I should say, let's call this some set S. Okay. S is essentially this set, right? The set in between this region in between. This is my S. Try to find the minimum distance between any point outside S to the hyperplane. I claim that that's going to be equal to t. Okay, so let's go back to the problem that we have at the moment, which is you minimize minus t subject to these constraints. Okay, so let's just try to solve this. Question? Yeah. Huh. You need to fix it, but as it will turn out, setting it equal to 1 or setting it less than or equal to 1 will end up giving you the same solution. That's one thing. The other thing is what I'm allowing you to do. So effectively you can scale alpha. When I say that the 2 norm of A is has to be less than or equal to 1, I'm allowing all solutions of A. So given a particular A, I'm effectively allowing solutions that can multiply both A and B by the same amount, but that factor has to be less than 1, less than or equal to 1, right? Which means that if I multiply both sides by both A and B by the same alpha, then that alpha has to be less than or equal to 1, which means that this alpha is less than or equal to 1. So the term multiplying this is greater than 1, which can only be better. It's no worse. Okay. So all solutions that you get from this, from minimizing this particular quantity, is greater than or equal to the width of this particular strip. So let me take a smaller number of points, say 20. Again, I have this particular set of points. Using the original approach, the approach previously, I would get so the pink line, the orange line is the solution that I get using my previous approach. So let me now I have 3 sets of variables, A, B, and T. What should I do? So I declare the variable T. my objective now is to not minimize a constant anymore, to minimize minus t or maximize t, the width of the strip. 2t is actually the width of the entire width of the strip, but half the width of the strip. And my constraints are x times a is less than or equal to b minus t, x2 times a is greater than or equal to b plus t. And what are the other constraints? Norm of a, norm 2 of a is less than or equal to 1, and t should be greater than or equal to 0. I get something, some solution, right? And in fact, the minimum value that I get, the minimum value of the objective function is effectively going to be the half the width of the strip, which in this case turns out to be 0.13 because I'm minimizing minus t. Now let me try to plot the same. But in addition, I also try to plot the entire buffer region. So probably too cluttered. This is clean, right? So given the two sets of points, my solution to the optimization problem is this red line. That's a hyperplane that separates these two. But the buffer region is described by the entire region between these two green lines, correct? And you can see that the green lines intersect with some points on each side, correct? And that's to be expected. If you want the maximum buffer, then they have to touch those two sets, right? So this is one solution, but let's also try to look at this problem in the dual form, right? What would the dual optimization problem look like? So this is my primal optimization problem. Okay, let's try to compute the dual. What is a Lagrangian equal to? How many Lagrange multipliers do I require? Correct. So n, capital N plus capital M plus 2. So I have Lagrange multipliers. I'll call lambda, the vector lambda, to be the Lagrange multipliers for this set of constraints. Lambda tilde to be the Lagrange multipliers for this other set of constraints. And I need something else. Let me say mu is the Lagrange multiplier for t greater than or equal to 0, and let me call it tau. That's better. So tau is a Lagrange multiplier for this constraint, and let me say alpha is a Lagrange multiplier for this particular constraint. What is this equal to? It's equal to the f0 of x, which is minus t, plus summation I equal to 1 to n, 1 for each of these constraints, lambda I times, what should it be? A transpose xi minus b plus t plus summation j equal to 1 to capital M lambda I tilde times, you have to be careful here. Remember, you always have to bring it to the standard form, right? So minus A transpose yi plus b plus t plus, correct, so tau times minus t plus alpha times 2 norm of all A minus 1. So how do I get the Lagrange dual? I have to minimize this over all possible overall A, B and T. So there's another variable that I missed here, which is T. Correct? So let me do this in steps. Let me first minimize this over B and T. What kind of a function is it in terms of A, B and T? Yeah. So this, the Lagrangian, how does it behave with A, B and T? Yeah. It's affine in B, affine in T, but it's not affine in A, right? Because of this constraint, I have this 2 norm over here. So it's not really affine. But whatever, it's going to be convex. Of course, it depends on alpha. So alpha is greater than or equal to 0, so it's going to be convex. Correct? Okay, that's good. What is the minimum of any affine function? It's going to be minus infinity, or it's equal to a fixed value depending on these constraints. So let me look at the minimum or the infimum overall B comma T of the Lagrange. So when is it finite? Maybe it will help to bring the terms corresponding to T together. So this is T times minus 1. What are the other terms involving T? It's summation lambda I and summation lambda I tilde. What else? Minus tau, right? What else? Plus B into so summation over J lambda I tilde minus summation over all I lambda I, okay, plus what remains. So let me bring the terms involving A together. Plus A transpose into, because this is a constant, right? I can write this as A transpose times lambda I xi. Because A transpose times summation over I lambda I xi minus summation over J lambda J tilde yj plus alpha times norm of A minus alpha. Correct? Okay, good. So now, when is the minimum with respect to this finite? With respect to B and T finite. I'll do that. I want to do it in steps, right? Because these are affine functions of B and T, but it is some other convex function of A. So what is the minimum equal to with respect to only B and T? Zero. When is it finite? When is this minimum finite? When this is equal to 0 and this is equal to 0. Correct? Okay, that's good. So, and when these two are equal to 0, what is the minimum equal to? There's still terms, right? It's going to be equal to this. So it's equal to this if these two are equal, which is summation over J lambda J tilde equal to sum over I lambda I, and this quantity is equal to 0, which means summation over I lambda I plus summation over J lambda J is equal to 1 plus tau. Okay, good. And it's equal to minus infinity otherwise. Okay. Do you agree with this? Good. So now I can try to minimize this with respect to A. How would I go about doing it? Equal to the last y. Why is that? How do you know that it's going to be the last? This term involves A, right? It involves a 2 norm of A. Correct. So even if I want to minimize over all possible A, and if I take A to be negative, in some sense, loosely speaking, I take A to tend to minus infinity because it's a vector. this quantity would kind of tend to, I could try to push this towards minus infinity, but then I also have this quantity, which is alpha times 2 norm of A, which tends to plus infinity. So it's not clear what the minimum is equal to, correct? But so how do we solve this? So in fact, let's consider a simpler problem. So let's suppose f of A is equal to A transpose some vector, let's call it x plus alpha times norm of A. Okay, what is infimum overall A, f of A? All we know is that alpha is, let's greater than or equal to 0. Overall A, right? X, I'm fixing the vector X. I'm viewing this as a function of A. Okay, if this is not comfortable, let me call this, say, U. Some vector U. Okay. I'm viewing this as a function of A, and I want to minimize this over all possible vectors A. Yeah. What is the gradient of norm of A? That's norm A squared, right? That's what I don't want to do. Sure, if I take the norm of A the whole square, then I'm going to get a different dual function. Right? I specifically wanted to take this because I want to find the dual of this particular function. I agree, both of them would end up being the same optimization problem. So what is the minimum of this? Remember that U is fixed, alpha is fixed. Let's consider one scenario. Okay, let me take A because I want to minimize over all possible A. Let me see if it is possible for f of A to go to negative infinity. Okay, under any circumstance, is it true that f of A is always finite, or can f of A go to minus infinity or not? Right. So what is 2 norm of A? This is equal to square root of A transpose A. Right. So f of A is equal to A transpose U plus alpha times square root of A transpose A. Let me choose A to be equal to alpha times U and try to minimize over all possible alpha. I'm minimizing this with respect to a restricted search space. So if this tends to minus infinity for some alpha, then obviously the minimum of f of A is also equal to minus infinity. So what does this f tilde of alpha, this is equal to alpha times U transpose U plus alpha, okay, bad notation, let me call this beta times U because I already have an alpha, So f tilde of beta is beta times u transpose u plus alpha square root of beta square u transpose u, which is nothing but beta times square root of u transpose u times square root u transpose u plus alpha. Right? Or let me do this a little more carefully. I want to look at the regime where this is beta is less than 0. Okay? Because I want to know if f of a can go to minus infinity or not. So if when beta is less than 0, this will end up being minus alpha. Correct? Because I'm taking this beta is actually negative. So when will f tilde of beta go to minus infinity? Which one?
Where the norm is less than,
Correct.
greater than,
If this is greater than alpha, then if f tilde of beta can go to minus infinity. So the infimum over all beta less than 0 of f tilde of beta, this is equal to minus infinity if norm of u is greater than or equal to, well, strictly greater than alpha, and if not, zero. Why? Yeah, in that case, this quantity is always non-negative, so this is equal to 0 otherwise. But this is over a restricted search space, right? So we can't really say that the minimum of f of a is also going to be 0 if norm of u is less than or equal to a, right? But in fact, it turns out that it is equal to 0 if the two norm of u is less than or equal to a. And why is that the case? Let's look at f of a. So suppose that the two norm of u is less than or equal to alpha. F of a is equal to a transpose u plus alpha times two norm of a. All right. I'll use the Cauchy-Schwarz inequality on A transpose U. What does that say? What does the Cauchy-Schwarz inequality say? What can I bound? This mod of A transpose U is less than or equal to norm of U times norm of A. Correct? But I can also say that the negative of mod of A transpose U is greater than or equal to the negative of norm u times norm A. So A transpose u is going to be greater than or equal to minus norm u times norm A. No matter what happens, this inner product is always going to be greater than or equal to minus 2 norm of u times 2 norm of A. So f of A is greater than or equal to is 2 norm of u, 2 norm of A plus alpha times 2 norm of A, which is 2 norm of A times alpha minus 2 norm of u. But 2 norm of u is always less than or equal to 2 norm of A, right? And norm of A is greater than or equal to 0. So this is always going to be greater than or equal to 0. So the minimum possible value of f of A in this particular scenario is going to be equal to 0, and that happens when A equal to 0. Okay, again, this is it's a bit of a trick, nothing more than that. But the main point here is that if you have f of A, which is A transpose some linear function of A, plus a 2 norm of A, then this is then the minimum of f of A is either minus infinity or a constant, depending on the coefficient, the normal vector, and this other constant. So to summarize, the infimum of A transpose u plus alpha times norm of u is equal to minus infinity if 2 norm of u is greater than alpha, and it is equal to 0 if 2 norm of u is less than or equal to alpha. Sorry, which one? There's no norm of A, right? I'm minimizing over A, right? So u is a constant here. Which one? Correct. Correct. So f of A is A transpose u plus alpha times norm of A. Correct? Oh, here. You mean to say on the left hand side? That's correct. Thanks. Correct. Of course, we took this detour, but coming back to computing the Lagrange dual, we wanted to minimize this over all possible A. No? So the Lagrange dual function g of lambda, lambda tilde, alpha, and tau, this is equal to so this turns out to be equal to minus alpha if the norm of this particular quantity is less than or equal to alpha. If the 2 norm of summation over I lambda I xi minus summation over j lambda j tilde yj if this is less than or equal to alpha, and I had the other constraints, which was that summation over I lambda I is equal to summation over all j lambda j, and I plus summation over j lambda j, this is equal to 1 minus alpha. Sorry, 1 plus tau. That's equal to minus infinity otherwise. So what is a dual optimization problem? Maximize minus alpha subject to these constraints. So maximize minus alpha subject to all of these constraints on lambda and tau. Right. Now with a little bit of simplification, you can kind of get rid of this tau. So I want summation over lambda I plus summation over lambda j to be equal to 1 plus tau. And I have these two constraints, right? Summation over lambda I. Okay, I have another set of constraints that lambda is greater than or equal to 0. Lambda tilde should be greater than or equal to 0. Tau should be greater than or equal to 0, and alpha should be greater than or equal to 0. Now these two are equal, correct? And the sum should be equal to 1 plus tau, which is the same as saying that this should be equal to 1 plus tau by 2, and this summation should also be equal to 1 plus tau by 2, correct? Now one way of interpreting this whole thing is, look here, you have some kind of a combination, a linear combination of all the points in xi, all the points in x. This is some linear combination of all the points in y. If both of these sum to 1, or effectively what we have is it sums to a particular constant, then it's the same as saying that you have a convex combination of points in x and another convex combination of points in y. And the norm of the difference between these two is essentially the distance, the minimum distance between the convex hulls of x and y. So the way to really interpret this is the minimum distance or scaled minimum distance between convex hull of x and convex hull of y. So these lambda i's would in some sense give you the coefficients, the convex coefficients, which correspond to the two closest points between x and y. Right, and all of these, just you can sort of simplify this. You'll ultimately get another constant in terms of tau and alpha. So if you try to solve for the dual optimization problem, instead of finding the hyperplane, you are effectively finding the two closest points in the convex hulls of x and y. And what would the hyperplane correspond to in this case? That the hyperplane would be the normal hyperplane to the point joining these two minimum distance points. So geometrically, I have this convex hull of x and some other set, which is the convex hull of y. The two minimum distance points would maybe be these 2 points. Right. the line joining these two is this, and the hyperplane separating the two convex hulls would effectively be the hyperplane passing through the midpoint of the line joining the two and exactly perpendicular to the line joining the two. That's kind of the insight that the dual optimization problem gives you. This is the classification problem in machine learning.
The dimension of the chain would be n minus 2.
The dimension of?
The hyperplane would be n.
Yes. Any other questions?
So if the summation lambda I and summation lambda tilde j are not one, then it is not really a convex hull that we are thinking.
Correct. It won't really give you the convex hull, but I can rescale lambda and lambda I and lambda j. Correct. I know that summation over all lambda I should be 1 plus tau by 2. Summation over all lambda j should be 1 plus tau by 2. Correct. So I can redefine lambda I and lambda j as summing up to 1, but then I take a scaling factor out over here. Another way to say that is I define some ui to be equal to lambda I, vj to be equal to lambda tilde j, then summation or let me say the following. I define ui to be equal to, let's say, lambda I times 1 plus tau by 2, vj to be lambda tilde j times 1 plus tau by 2. Okay, you use this alternate parameterization and try to see what this turns out to be, what the dual optimization turns out to be. With this parameterization, you will see that this quantity, the objective function here, is a scaled version of the minimum distance between the two convex hulls. Okay. Any other questions? All right. So if not, let's stop here.